Yeah, so for announcements for today, so you guys should have already turned in homework 1, and homework 2 will also be up soon, and this one will definitely be a little tougher than last week's and definitely be a little longer. So definitely try to start early on that. And office hours, same as this week basically. So check B courses for the times. They'll be like the same for the semester. And it's the same Zoom link as lecture. Okay, and so today we'll be going over dictionaries and recursion. And I think the attendance form is in the chat. So if you guys could fill that out, that would be great. Yeah. Okay, so last week we talked about if statements. And so if you guys remember, this is basically like to split your code up into multiple cases. So like in this example, we have if x is greater than 10, like print this statement. And if like x was like less than 10, then we would have skipped over this whole clause and gone to like the else if statement. And then also the else statement. And so it's always like top to bottom, and you just check your like input against each of these statements and execute whichever one is like true. Okay, and so to like kind of review what we learned about last week, I'll be making some breakout rooms so you guys can just talk about like what while and for loops are, just kind of remind each other like the structure of each of them and like what kind of different cases would you want to use each of them, like how are they different. So let me just open up some breakout rooms. Yeah. Okay, I think pretty much everyone's back now. So, okay, yeah, so does anyone want to share like something about while or for loops and like maybe a difference between them? Or maybe just like say like kind of the structure of a while loop or like how you would use a for loop, like anything about either.
We talked about how for, like, in my opinion, for loops, you would kind of use them to go through something like a list or a string. But with a while loop, you would kind of use it to do something under a certain condition.
Yeah, that's perfect. So basically the difference is like here we have like while loops, and basically you do like the stuff inside the while loop like while the condition is true. So like you guys like learned last time, like booleans, like doing the double equal sign to check if something is equal. And with while loops, you also have to like change it yourself each time. Like if you have a counter, you have to increment or decrement that each time in the loop. And then with for loops, it's like Megan was saying, like you basically you go through a list, and for each element in the list, you do like the stuff inside of here. So in for loops, you don't actually have to like increment or decrease a separate counter. It like kind of does it for you. Yeah, and so and a lot of times you can like use both of them for the same thing. Like if you even if you want to go through like an array, you can use a while loop or a for loop and just kind of format your code a little differently. But in general, like while loops you see in like video games, like something about like passwords, you know, like simulations, and sometimes like if your steps don't need to be a discrete integer value, or if you want to like, so you can like increase your steps by like 0.5 each time and stuff like that. And then for loops are mostly for like going through large data sets. So if you wanted to like change each element in like a really large data set, you could do that. Grid simulation. So if you have like a 2D matrix, like a square, it's really easy to use for loops because you can have like 2 for loops kind of nested in each other. And so you'll also see that a lot. Yeah, and then for loops are also more like discrete integer steps. Okay, and so then today we're going to start going over dictionaries, which are the last built-in data type of Python. So we've already talked about like lists and tuples before. And so today we'll be talking about dictionaries. And these are really powerful and also like really common as well. And they're basically made up of key value pairs. So if you see like in this flight dictionary example, Yeah, so if you see in this flight dictionary example, we have like the keys in red. And so it'll be like name, age, and class. And each of these keys will correspond to a value. Here it's Zara, 7, and first. So if you kind of think of like an actual dictionary, like that you would look up a word in, like say I want to look up the word hello, the word hello would be kind of a key, and the value associated with it would be like the definition of hello, which would be like, you know, a greeting or something you say like when you want to say hi to someone. And so basically you use a key to like look up something in your dictionary, and then the values are like the definitions associated with a specific key. And so if we want to create a dictionary, you can kind of do this in two different ways. The first way is like you initialize kind of an empty dictionary using the curly brackets or using dict parentheses. Like this is kind of like a built-in function like max or min, and Python like already like recognizes the word dict. So you don't have to like do anything special with that. Yeah, so if you see in this first line, these are two ways to initialize the flight dictionary. And then obviously, you know, we don't just want an empty dictionary, we also want to add some values. And so how you would do that is by using this notation of using your dictionary name, and then you use like the normal brackets with like your key in here, and then the value you want to associate to it. And so one key basically maps to like one value. And keys also don't necessarily have to be strings. Like this could have been like dictionary 7 equals Zara, like for some reason, if you wanted to do that. Yeah, then the second way to make a dictionary is you can just initialize the dictionary with the values in it from the start. So if you already know like all of the keys and values you want, you can just do that. And you can also use like the dict keyword again. And this is like a really interesting way using like the dict keyword around a list, because like maybe you like found a data set online that has all of its data already structured in a list with like tuples inside of keys and values, then it's really easy to just call dict on that like list. Yeah, and so after we've made our dictionary, if you want to look up some values from it, you can look up the key by doing flight dictionary name. And so since name was the key, it'll return like Zara, which was the value associated with name. Same with age, it returns 7. And you can also use like the keyword .get. And so like the dot notation basically just means like it's like another function like we've seen before, like because you can tell by the parentheses. And it basically says like from this dictionary, the function will return the value associated with like the key you put in. And so these are like the two ways that you would access values from your keys. And then also like if you want to delete keys, you would use this word called del. And so this like does it in place. So if you just type in del flight dictionary name, it'll delete the name Zara pair. So it'll delete the key and the value. Yeah, and then also if you want to like, if you want like all of your values in a list, you can just call like your dictionary name dot values with like nothing in the parentheses. And so this will just return all of the values of your dictionary in a list. And same with the keys, you can call dictionary.keys, and this will return all of your keys in a list. So you can like see them or organize them if you want. But yeah. Yeah, and so obviously since, you know, this is an astrophysics kind of DeCal, like a more relevant example is, so for like say the supernova 1987A, you can make a dictionary of like the apparent magnitude, distance, RA, dec, and type. And so here like the keys would be apparent magnitude, distance, RA, dec, type, because those are on like the left of the colon. And the values are like the 2.9, 51.4, like everything on the right of the colons. And so we can do like a quick demo of this. Let me just put that. Okay, so let's say like I wanted to make a dictionary of like all of the planets in our solar system and like how many hours like are like a day in length. So like, let's say I wanted to make a dictionary called planet days. I could initialize it like this. And so that would just make an empty dictionary. Oh wait, yeah, and then so now let's say I wanted to add like how long a day on Earth is. Like, so does anyone like tell me like what should the value pair be? Like if I want to say like how many hours is how long is a day on Earth? Like that's just like 24. So if I do this, this should now initialize like my dictionary and add that key in. So if I call my dictionary again, you can see I have like this pair in here. But like obviously since there's like 7 or 8 planets in our solar system, that's like kind of annoying to like type out each one individually on each line. So since I already have this list here of all of the planets in our solar system and their corresponding hours, I can just take a shortcut and do planet days equals dict of this list I have, since it's already in like tuple form. So now I have a dictionary of all of my planets and like the length of their days. Does anyone have any questions so far? Or like you want me to like go over anything or like go back to a slide? Or I think I haven't been looking at the chat. Yeah, okay. And so let's say now that, like let's say I realized that like, oh, like the length of a day on Earth isn't actually 24 hours. Like it's actually like 48 hours for some reason. So like, how do you think I can go and change it? Does anyone have any ideas? Okay, so a quick way that you could just do this is you would just make another entry, but with the exact same key, and that'll just overwrite it. So if I do this, we can see that in the value for Earth is now overwritten to 48. So like it always takes like the last kind of value you put in. So you guys also want to like be mindful of that and make sure that you don't like overwrite anything accidentally. And because like you can also only have one key in your dictionary. Like I can't have 2 Earth keys with like different values. So yeah. Yeah, and so now like if I wanted to actually look at, if I wanted my dictionary to not just show like how many hours a day is, like how long a day is, and I want to see it more as like a proportion, like compared to Earth, like I could make, I could organize, or I could like modify my dictionary so that everything's in terms of like how long an Earth day is. So like, you know, if like one of the planets had a day that was 48 hours long, it would be like the value 2 instead of like 48. So I could like show everything as a proportion. So to do that, like, does anyone know of a good way that I could like kind of like something we've learned before where I could iterate through like something in a list? Like what structure did we talk about that does that?
The for loop?
Yeah, exactly. So we can just do for, and since we want to iterate like over each kind of key value pair, we can do for planet in planet days dot keys, since this like planet days dot keys is a list. And so now we can change it by saying planet planet days planet, and then we can do divide by 24 because that's like the length of an Earth day. And like this divide equals thing just means take planet days planet and divide that by 24, which is just kind of like shorthand and makes your code cleaner as well. So if we now print this, we should see that everything's in terms of like Earth, like an Earth day. So basically like Mercury is actually like one day in Mercury is 59 Earth days, and Venus is like 243. So like, yeah. So yeah, that was just a quick demo on dictionaries. Does anyone have any questions about that? Okay. So now let's talk about the next topic. Okay, so this is also another quick thing. Like we've kind of gone over all of the really basic things of Python now. And so like the rest of this lecture will just kind of be like more advanced topics, extra things that you don't necessarily have to like master right away, but it's just so that like if you ever see it, you won't be too confused and you can kind of like reference these slides again. And yeah, just to like think about for a while. But I think we showed this also in like last week's lecture, and these are called Lambda functions. And they're basically a really quick way of making a function. So instead of writing like def quadratic, you can just say quadratic equals lambda x colon x squared. And so this would be the same as writing like def quadratic parentheses x and saying like return x squared. And usually you would just use lambda when like the function is like one line. So it's really easy to put in one line. Yeah, and like the lambda is a special keyword. So like you don't have to like do anything special before using this line. Like Python already knows that what lambda means. Okay, and then moving on to the topic of recursion. This is also a pretty complicated topic. And if you really want to like learn a lot more, go a lot more in depth, you guys should like, I would definitely encourage you to take 61A. Like it's actually a pretty fun class, even though it's kind of like intimidating at first, but yeah, definitely take like more CS classes if you want to learn more. And basically like the idea of recursion is that instead of like returning like at the end of your function, like return x squared or like return the number 2 or return true or false, you basically return the function itself. And so say something like this example of like x equals square root of 6 plus square root of 6, like ... We can essentially code this because like you kind of call the function itself and it has like this really nested structure that repeats a lot. Yeah, and so you might be wondering, how do we implement it? Because it seems like you would need a lot of code to write something that kind of like loops over and over, but it's actually really, really short. And so the main idea behind this is called like a recursive leap of faith. And you basically have to trust that your recursive call will eventually meet your base case and like return exactly what you want. So if you look at factorial, which, you know, as we all know, like factorial of n would return like n times n minus 1 times n minus 2 all the way to 1. So like factorial of 5 would return like 5 times 4 times 3 times 2 times 1. And so in this function, we basically split up our recursion into like a base case and a recursive case. And so the recursive case, as you can see, it calls like it returns n times like another call to itself. And so this will mean like if you call like factorial of 5, it'll return 5 times factorial of 4. And you can kind of see how like through that, it'll like end up calling factorial like a bunch of times just to do like one output. Yeah, so basically recursion will always return a call to the same function. And so like more formally, the recursive case is what is like the return statement at the end of the function. And you always want to make sure you modify your argument slightly, just like in a while loop, because if we like just keep calling the exact same function with no change to our arguments, this will just be like an infinite loop. And then we also have the base case, which is basically like so in recursion, your recursive call will make like a bunch of like new calls to itself. And so this will go on forever unless you have a base case, which is at the end of the long chain. And it'll signal that you want to finally stop all your recursive calls and start like returning values. So it's kind of like this like picture here. When you make your recursive call, it'll open up another frame. And so it'll basically be like an identical copy of like the same function. And then like at the very end, your base case will kind of like signal like to stop, and then it'll kind of like bring everything together. So in a way, you kind of have to trust that it'll just work, because like you're not really programming yourself like every single step, but you're just basically starting like, you're saying like, this is the beginning, this is the end, and then you just have to trust that they will like meet. Yeah, so if we look at factorial again, so we know factorial of 5 is 5 times 4 times 3 times 2 times 1. So if we like, we can actually trace like the calls ourselves. So let's say we start with factorial of 5. We so our input n is 5. So we look into our function and we say, does 5 equal 1? And so since this is false, we go to our else statement. And then from this call, we return like 5 times factorial of 4. So then we now look at factorial of 4, right? And we say n is now equal to 4. So is 4 equal to 1? And since that's also false, we go to the else statement and we say like return 4 times factorial of 3. And so basically this factorial of 4 here is substituted with, so basically we can kind of substitute this in with 4 times factorial of 3. Okay, and so then we keep going. So now let's see with, with 4 times, and then with factorial of 3, we again go back to our function and say, does 3 equal 1? And so since this is still false, we go to our else statement. And so for factorial of 3, like right here, we use like 3 times factorial of 2. So can someone tell me like what our next line should be, like in our kind of recursive stack?
Five times 4 times 3 times 2 times factorial of 1.
Yeah, exactly. Okay. And so now that we have factorial, oh wait, I missed a 2. Okay, yeah, so now that we have factorial of 1, we look here and finally we have like 1 equals to 1. So this will return 1. And so we'll finally start kind of like returning our statements. But since like this is technically like we're still in the factorial of 1 call right now, right? So actually the computer won't just like evaluate all of this at once. It'll kind of evaluate it from here, because that's where like it'll return. So it finally returns factorial of 1, and that goes back into factorial of 2. So now factorial of 2 has like the 1 value, so it can return like 2 times 1. And then factorial of 2 will like return this to factorial of 3, which will like return 3 times 2 times 1. And then this will like go all the way up until you get to like factorial of 5. So basically it'll go like 5 times 4 times 3 times 2. And then it'll go 5 times 4 times 6. And then 5 times 24 until we finally have 120. And this will be like your final return value. So kind of like you can see like the calls like open up and they'll all be like, so each factorial will have like an open call. And then the last one will finally close, which will then close all the rest. So it's kind of like this like diagram here of like all of the calls opening, and then you're like finally like closing. Yeah, so does anyone have any questions so far? I know it's like pretty confusing to like look at and also kind of hard to come up with yourself, but this is just kind of to like introduce you guys to the idea, and yeah.
Yeah, I have a question.
Yeah.
So we were able to like figure this out because it was factorial of 5, but what if it's like a factorial of like 1,000?
Yeah, so basically, like factorial of 1,000, obviously like we won't have to write out like this entire stack ourselves, but basically like in the computer, like that's what's happening. Like the computer will open up like 1,000 function calls and then close like 1,000. And like computers operate really, really, really fast, like much faster than we can. So like we won't really notice this. It'll still like return in just like a couple of seconds. But yeah, so it's like the same thing, just a lot like more stack.
Also, like just a note on factorials, especially a factorial of a large number. Sometimes you will get an overflow because like the computer just cannot take that like such a large number, say like 1,000 factorials. Sometimes it's the limit. You cannot do more than that, like no matter what. Yeah, but as we go like later in the semester, you will notice like you don't have to like write factorials in this form. There are easier ways, but for now, just use this.
Yeah, like the computer has like other things that it'll calculate for like really, really big numbers. But if we want to write it ourselves, like this is what we would do. Yeah, and so like also you guys like might be thinking like it might be easier to write factorial of like a while loop because you can also just increment your counter, right? And so those are basically equivalent. Like recursion isn't like any slower than a while loop. They're around like the same speed. It's just like kind of difference of how you want to like present the code. And yeah, so it's not like you guys have to like force yourselves to use recursion whenever you're coding, but it's just so, like if you guys do see this, like you can kind of understand what's going on. Yeah, so like why we would use recursion are that some ideas are just better expressed as small steps. And so a lot of times you can use while or for loops, but it might be easier to represent it with recursion. And there are also a lot of times when we definitely will need recursion, not really in this class, but like if you go into like other CS classes, like things like tree recursion to express multiple paths, or like there's also some algorithms in CS like divide and conquer that you need to use recursion with. But in general, it can also make your code a lot cleaner and efficient because you only need like a base case and a recursive case. You don't really need to code every single step in between. Yeah, okay, so now we can like go through a bunch of examples and then it'll make like a lot more sense. Okay, yeah, so I think one good example of recursion is like the Fibonacci sequence. So like, can someone tell me like kind of the first few numbers of the Fibonacci sequence or just like the rules in general? Okay, I can get us started. So like with Fibonacci, you start with like your two kind of base values of 0 and 1. And then like kind of the pattern with the Fibonacci sequence is that you have to add your previous two values and that's like your next value. So our next value here would be 0 plus 1, which is 1. And then if we keep going on the pattern, like 1 plus 1 is 2, and then 1 plus 2 is 3. And the next value would be like 2 plus 3, and so this would be 5, and so on. So yeah, so like this is an example of like where we could use recursion to clean up our code, but we can also write it using a while loop. So for our while loop, we would want to start with like 0 and 1, right? Because those are kind of the values that you have to start with. So we can say like fib1 equals 0 and fib2 equals 1. So then we can use our while loop to to basically like keep adding the previous values until we get to like n. And so in our function, we want to return the nth Fibonacci number. So like if n was like 3, we want to return 2 because this is like the third Fibonacci number if we index it like 0, 1, 2, 3. Yeah, and so we'll definitely need a counter so that we can kind of count up to our end value. So we can start at 0 and say while k is less than or equal to n. We want to like continue our Fibonacci pattern. Yeah, and so to get our next value, we would like use our pattern of adding the two previous numbers. So we can say our current value is fib1 plus fib2. And now that we have like our current value, we need to update our previous two values. So now like fib2 should now be so like fib1, instead of being like, if we start at 0 and 1, fib1 should now become 1, and fib2 should now become 1. So we can also put that into code. Yeah, and so then at the end of this, we just want to return our current value. And if we try that out, we should get the correct value. So like fib while of 5 should return, or fib while of 4 should return 3. Wait, okay, and so like here, really common mistake, I forgot to like increment k, and so that's why like nothing was outputting, because like it was like doing kind of an now fib while printed 1, 2, 3, 4. I think I just have an indexing issue. Yeah, so this should just start at 1. And then we have fib4 is 3. Yeah, so now if we want to make this recursively, we need to start, like, I think a good place to start with writing recursion functions is at your base case. And so for like your base case, you kind of think of it as like the smallest input fib could have. So like, let's say like our fib recursive function took in 0. Like, what should the Fibonacci number be if it's just like fib 0? So that would be, so obviously that's our 0 Fibonacci sequence number, which is just 0. So we can kind of use that as our base case. So if n is 0, we just say return 0. And then since we kind of have like two base cases, like 0 and 1, because those are just kind of the values that like weren't really summed from previous things, right? So we need to have two base cases in this case, and also say if n is equal to 1, return 1. Yeah, and so for like a lot of times the base case is usually kind of straightforward. You just need to think of like your smallest example and just do what your return value should be in those cases. And like for Fibonacci, we'd have to think more on the recursive call. So this one, instead of like, so we know we want to do some sort of recursive call to fibrec itself. And so we also know it's like kind of the idea of you want to sum your two previous values. So let's say we have like our Fibonacci number, our current Fibonacci number is like 8. Like the way we got 8 is by adding 3 and 5, which is our previous value and like 2 previous values ago. So if we just kind of write the logic of this, it's basically writing like what fibrec of n minus 1 would output. So like our previous Fibonacci number added to like our Fibonacci number from 2 previous steps ago. And so it looks really confusing if we write it like this, but if you just think about it, we're basically like saying, like we're basically trusting that fibrec of n minus 1 returned like the correct value. And that's like our previous Fibonacci number. And fibrec of n minus 2 like also correctly returned like our 2 previous numbers ago. Yeah, so then we can test this out as well. Yeah, so as you can see, this is like also 3. Do you guys have any questions on this example? Or like, you want me to like explain any of the of the code again? Okay, so we can go on to another demo. So like earlier on the slide, like we said that we could compute like this thing, right? So now like we can actually try to like write it ourselves. Yeah, and I guess like this is kind of a pointless thing because I'm not really sure why you would ever want to compute this, but we can just kind of like do it for fun. So does anyone like have any ideas for a base case or like where to start? So, okay, if we know our smallest input should be like 0, what should we return in the case that like this is 0?
The square root of 6.
Yeah, so like we could say if n, or I guess that'd be, yeah, so I guess like that'd be for if there's like 1 time. Yeah, because if we compute the square root of 6 like 0 times, that'll be like 0. But yeah, for like the other base case, if n equals 1, we want to return square math dot square root of 6. Okay, and like the reason why we use math dot here is just because like there's no built-in square root for Python, so you can just like do import math. And if you like ever are not sure like if you can use a function, you can just like Google it and like Google like what libraries have it. Okay, so now for our recursive, like so basically now we've written the case where like this very inner loop of square root of 6, right? So let's say we wanted to like do this twice, like this pattern twice. So it's like basically changing our code from just this like very inner loop to now like one more layer. And we would do this in our recursive case. So you can think of like this box as just like our square root of 6 plus like the function call. And so we need to think about like what we want to have, like how do we represent this like on the left here? Does anyone have any ideas for like the recursive case? Or you know, just like a guess is fine, or like just any idea to kind of get us started.
Just a good rule of thumb, anything that's not a base case is usually going to have to call the function itself. So since this like last part is not a base case, it's definitely going to have to do something with calling the functions squirt 6 plus.
Okay, yeah, so we can kind of just like go off of what James said. So we're definitely going to need to call our function square root 6 plus. And so we know that since our base case is like the very smallest number, and we definitely need to change something from call to call, we can just start this as x minus 1. And then, so if you've actually noticed here, like in our, like the rule we want to code like has plus signs in it, but we don't actually like add anything here. So if you think about it, if we have like a square root 6 on the inside, we basically need to do square root 6 plus like what we have on the inside. So like the rest of our line here can just be math dot square root of 6. And then we can just add that to like whatever square root of like our recursive call to the function returns. And so this way we'll have like a nested structure. So now we can test it. So if we just like test 1, oh wait, name and is not defined. Oops. So yeah, you just need to be consistent with your arguments. Yeah, so since I have x here, I should have also had x for the base cases. Yeah, okay, so now we have our square root 6 plus, we'll just return square root of 6. And so now if we like try to increase it to like 2, we get like 4.8989. Oh, actually, yeah, actually, so this like, I think we messed up a little bit here because this is like, here, like our nested square root sign, it's like the square root of everything inside it, whereas here we like only have 6 inside the square root. So we can just change this by moving one parenthesis outside. And so we get 2.9. And then we can confirm this on like Desmos or something. So, okay, so if we have square root of 6, that's just 2.4. And then if we add like one more kind of loop to that, we can do square root 6 plus square root 6, and then we get like 2.9, just like we have here. And then if I increase this to 3, we have 2.984. And then here we can also add another loop to it. And then like, I think someone had a question before, like, what if we actually had like 1,000 or something like that? So we can also try that. So if we have 100, this actually goes to 3 because I guess like this weird pattern converges. And then same if we have like 1,000, it's like still 3. So you can kind of see how, like even if you do like 1,000 calls, it'll be really fast. But like if we add like another 0, then it actually starts to take a while just because like that's a lot for a computer to do. And yeah, like Elin was kind of saying before, this one we actually get an error just because this was like too many frames for the computer to compute. But usually anything that like you'll have to do definitely won't be as complicated as like 10,000 calls to this. But yeah, okay. So does anyone have any questions from like lecture today or like anything reviewed from last time? I can do another demo if you guys want, or if like anyone has any questions they'd like to go over.
If there's no questions, I just wanted to make an announcement about the homework, if that's okay.
Yeah, go.
Okay, so yeah, for the homework 2 is posted. I posted it last night. I just want to give everybody a fair warning. It's harder than the first one. It will be harder than the first one. It will require a bit more time, so don't save it for the last minute. I made one of the questions optional this year, so hopefully that'll make it a little bit less difficult, but just know it will be quite a bit more difficult than the first one. And the reason for that is because I want to make sure that you know that like our homework isn't like a joke, and that like you should actually spend some time every week doing it. And because the only way you'll really learn how to code is by doing it yourself, not by listening to us all the time. So just make sure you start your homework a bit earlier, so that you're not thrown off guard when you go to start your homework and it's like the last day and you're like, oh no. So just fair warning, it will be a little bit more difficult, or not a little bit, it'll be a bit more difficult this time, but hopefully nothing too atrocious.
Yeah, and one last announcement. There's like an Astro event tomorrow, like Thursday, 5 to 6 p.m. And one of the professors, like Eugene Chang, will like, he'll give basically kind of like a faculty talk. And I think it's kind of like a conversation, and Elin's actually hosting it. So you should all go because he's a pretty cool and funny guy.
You guys should go for 2 reasons. Firstly, I'm the host. That's the most important reason, apparently.
Yeah.
Secondly, because it's Eugene. When you actually get to operatives, maybe some of you already are. When you actually get to operatives, you will meet Eugene if you take Planet. And so what I heard when I was the first year, there was this person who told me, like, if Eugene ever teaches a class, no matter what it is, like just take it, right? So, and also like, if you don't like Planet, you will never meet him. That's pretty much the case. You will most likely not meet him. So, but once, like, yeah, like just once over like your 4 years in Berkeley, right? Like talk to him. Go to the event. I will send out a link, or maybe some of us will send out a link in the Recursive announcement for like the event tomorrow. It's 5 to 6, right? Yeah. Tomorrow, yeah, 5 to 6. Yeah. So yeah, I don't even know what the link is. So yeah. Yeah. So yeah.
Okay.
Okay, yeah, so that's all we have time for today. So you guys are free to go.
Thank you everybody for coming.
Yeah, thank you.
Thank you.